So hello everyone. My name is Yilin Yang. I'm also a PhD student at WinLab, and I'll be talking about one of our research works, which is titled EchoLock towards low effort mobile user identification, leveraging structure-borne echoes. As you're probably aware from the name of this session and also from the related works beforehand, we're interested in securing the IoT, but also specifically from the perspective of user identification techniques and their role in mobile devices and all sorts of digital devices. I'm sure it's no exaggeration to say that it's deeply integrated into all of our lives. All of our information these days is highly digitized. We have to access many services online, such as financing, banking, our health information, our emails, registration, even signing up for this Zoom seminar. I'm sure we had to go through some identification process, whether it was through email or entering the meeting password. So all of this is to say is that user identification is heavily integrated into many of our services that we use. And so at least by the estimates of some surveys or studies on cell phone addiction, we're going through these user identification techniques dozens or maybe even hundreds of times per day. All of it just to access our everyday information and to conduct our errands or enjoy our own leisure time. And so in the best case scenario, we may not even think about this consciously too much because the process is so seamless, whether we're just pressing a button or typing in a password, and then that's it, and we can get access to our information. But on the other hand, maybe the process is not so smooth, and so we end up in cases where people may get frustrated or locked out unintentionally. And as we even heard in some of the earlier talks beforehand, the amount of delay that we have on these services is very important because no matter how effective your security may be, if it's very troublesome for the user to use, you'll have a hard time having other systems to adopt your proposed technique. So this highlights a lot of concerns for how we want to develop user identification for the IoT. And so we can sort of outline a few spectrums of how good or bad user identification can excel with by certain metrics. And this goes along with the lines of how much of the process we want to impose upon either the human user or the computer or the device. And so on one end of the spectrum, you may try to have all of the, or the majority of the workload imposed on the user. Say by entering your login information, the user has to remember their password, their login information, type it correctly to enter it in. And so on one hand, this ensures a simple mechanical implementation because you simply need to verify your input parameters. But of course, I'm sure many security analysts could confirm this, but oftentimes a large source of failure within security systems would be the human element. And so there are many possibilities where the user may forget information or enter information inaccurately. And so there is the need to make this process convenient and easy to use, which can be offered in the form of, say, like memorizing your credentials. Now, on the other end of the spectrum, you may try to have the machine or the computer perform the majority of the workload in authenticating the user. And now in this case, we are removing a lot of the effort from the user in that they don't need to interact as much. Say for the example of camera-based identification, the user simply needs to hold still and then we can have the machine or the AI scan the user and then confirm their identity. But of course, now we are imposing the burden on the computer and in such a way that it has to be accurate and fast. And in the case where it is not, it can be very frustrating for the user experience because they may be sitting idly by, not sure whether the system is working correctly. And then after several seconds, they may either find out it worked or worst case, it did not work. And so this causes a lot of issues when you're trying to automate this type of security system. And so we can define this sort of usability trade-off where you're trying to balance simplicity and complexity while also at the same time optimizing the accuracy of your security and user identification. Now, on the one hand, if your system is, say, too simple, you may run into issues where the security offered is not very strong because people may simply use very, very insecure credentials, such as short passwords 123. But on the other hand, if you are developing a very complex user system, either it could be very slow or it may be so imposing and intimidating to use that the user may indirectly compromise their own security by simplifying the system in their own hands in an unsecure manner, such as by writing down very long passwords and leaving them out in the open. So all of this is to say is that there are some very there are a lot of things that we want to achieve for a user identification to be secure, fast, convenient, reliable, and not very complex. But of course, it's difficult to meet all of those demands simultaneously. So this leads us to reflect on how some of our existing user identification technologies perform by some of these metrics that we just mentioned beforehand. So probably the most common example that we're all aware of is knowledge-based verification, which is through commonly seen in the form of typing in your passwords, or perhaps on like smartphones, you could be swiping in a pattern, for example. And this is a form of identification where we're not necessarily confirming the identity of a person, we're just checking for if a piece of information has been presented correctly, which has its own benefits. Probably most obviously, this is a very simple and easy technique to implement, but of course, we're not necessarily proving your identity because multiple people could know a password, for example. Now, to address this, we have a lot more biometric-based information that have been used as credentials in recent years, especially on our smart devices, such as facial recognition or voice recognition. So these are all technologies that are truly measuring qualities about the person's actual identity, such as the appearance of your face, the sound of your voice, or any keywords you might utter, or also more specifically, very fine details about the body, such as the fingerprint or the patterns of your iris, which are known to be unique to individuals, even if it is just a very small part of your body. Now, all of these techniques have been widely used and they're all known to be secure and very popular. But one attribute that we note in all of these technologies is that they all require active participation of the user, even if briefly, such as by typing in the password or posing for the camera or saying a word or pressing a scanner button. All of this demands the user's attention, it requires their participation, and this can potentially interrupt their access to the services. This presents the sort of latency or delay where you're still being stalled, however briefly, to access your information. And this may be fine in most cases, but this inspired us to seek out if there are better alternatives that we could implement. So what we're proposing in this work is that we can try and implement a form of passive or low effort method of user identification. Now, to sort of sell this concept, if you were to say consider a smartphone, probably the conventional way of unlocking it and passing the user identification process is that you would have to say pick up your phone and then swipe in your pattern through the navigation lock screen. And then maybe then you'll be unlocked and then you can have access to all of the information on your phone. But wouldn't it be nice where instead of going through that whole process, you could just simply pick up your phone and then your phone will understand who is holding them at the exact moment in time. And this is theoretically possible if your phone can detect like the person's identity, like for example, the hand that is holding them. Now, the question is, how can we realize this theoretical idea into a practical reality? And so our idea is to perform passive acoustic sensing of the hand biometric information. And so what we're using, and specifically, is sound, yes, but specifically structure-borne sound. And structure-borne sound, if you can imagine, is related to airborne sound or vibration patterns, where if you imagine traditional sound waves as, say, emanating from some sound source, like a person's speech or maybe a speaker, and then that these sound waves can bounce around in a room, reflect off surfaces, and then they are received by some endpoint, such as your ears or maybe the microphone on a device. Now, this behavior is also similar for structure-borne sounds, but rather than traveling through airborne paths, they are traveling through solid surfaces, and these are known as the structure-borne paths. And these structures can be objects such as tables or walls, or even the device itself that's creating the sound, such as your smartphone. And now these structure-borne sounds, they can be impacted by external forces, much in the same way as airborne sounds, and that these forces can include people, for example. So the reflection of structure-borne sound off of a person's body or their hand, for example, will also produce some type of impact in the reflection. So what we're suggesting is that different people may produce unique impact on these sound waves. And so it is possible to identify different users based on the interactions they have with structure-borne sound. And so if you were to build, say, a machine learning framework, you could detect these differences in the sound waves of the structure-borne sound. And in doing so, recognize different identities based off some training labels, and then perform the identification process passively without any interaction. So as you can sort of imagine from like this little diagram on the bottom here, just by holding the device with your hand, your device could say play a sound, and it will travel through the structure of your device. And in doing so, it is captured by the microphone. We can detect this information in order to unlock the device, or in other application scenarios, unlock other apps such as your private messages, your emails, any banking apps you may have, or maybe just to customize your personal settings if you're using some smart device that's shared by other people's. To describe this idea in a little bit more detail, we can sort of show the behavior of structure-borne sound. So if you imagine your device that's emanating your acoustic signal, you can have your speaker play some acoustic signal, and then it will travel and propagate through different mediums. Now, this includes traveling through air, but it will also travel through the physical object, like I mentioned earlier. So if you imagine that airborne sound is bouncing and reflecting inside a room, you can imagine that the, say, like the device itself is also some type of microcosm of a room, where the structure-borne sound will be bouncing inside the device until it reaches the endpoint, which would be the receiving microphone. Now, this means that your structure-borne sound may have some sort of natural or neutral behavior, but if the state of the structure is modified, say by the external forces acted upon it by a user's grip, say the compression of the hand, how you're holding the device will change the behavior of the structure-borne sound propagation, because the structure itself is being modified. So instead of having just your base device lying on a table, for example, now where the structure is the base device being held by the grip of your hand, which changes the shape of the structure, because now it's not just a rectangle for smartphones, it's a rectangle with some extrusion along the side of it by your hand. And that hand is also exerting a physical force. This will change the propagation behavior and dampen the signal, actually. So this is sort of comparable to perhaps musical instruments, where if you were to say hit a drum and that the drum surface vibrates, that can be a neutral state. But if you are pressing against the surface, this will dampen the amount of vibration and the behavior of the structure-borne sound, such that when you hit it, now you will be getting a different sound. This is the intuition behind our idea of sensing the identity of a user based on the forces exerted by their hand. And we're using different devices as examples. In the context of this talk, we'll often be referring to smartphones as a common example. But the idea is possible to implement simply just through using a speaker and a microphone, two very common sensors. So it's possible that this idea can also be implemented not just on your own common smart devices, but all sorts of different devices, including tablets, your phones, any small objects such as maybe like wireless mouses or smart remotes. As long as it is possible to affix, say, these sensors, the speaker and microphone, we can perform all kinds of structure-borne based sound sensing. Now, this idea may be interesting, but we need to verify the principles of this idea, being how we can extract the structure-borne sound, because it's rather different from the airborne sound collection that many other acoustic works perform, but also to verify whether this technique can be reliable in distinguishing between different labels, such as user identities, and also the effectiveness of how securely we can protect private information with the security system based off this passive form of structure-borne sound sensing. So we look at, say, some very preliminary examples. Now, this isn't an example of user identification, but more so the behaviors of structure-borne sound in different scenarios. So we can outline three very, very broad and distinct scenarios, such as a device being held in a hand, resting on a table, or being stored in a pocket. And the reason for these scenarios that we've chosen in this example is that they should all theoretically produce some very different behaviors, because there are different degrees of forces being acted upon the solid material, the smartphone in this case. So for example, there would be minimal force exerted on a table, whereas if you're storing the device inside a pocket, there's a lot more compression and muffling of the sound, which should produce some unique patterns. And so we can actually verify this observation through this sort of matrix that you see here, where we can extract the Euclidean distance of some samples of structure-borne sound by measuring their amplitudes. And we can compare these samples from different scenarios, and also comparing them with samples from the same scenario. So what you see in the chart on the left, for example, is that the Euclidean distance of samples taken from one scenario, such as samples taken from structure-borne sound samples taken from the device when it's being held by the hand, they're all very, very similar to each other with very low Euclidean distances, but they're also very distinct from samples collected from these other scenarios, such as from the table or the pocket. Specifically, more extreme differences between the hand and the pocket, which shows that there's a degree of granularity that we can detect these differences. But and that's all well and good, but for the goals of user identification, where the scenario is much, much more similar and finer grained, we're not trying to differentiate between hands and tables. We're trying to differentiate between different hands, which can be much more challenging. But even in a small scale example, say just by testing two different hands, we can see that this same sort of intuition can be observed on the chart on the right here, where if you were to take several samples from person one and person two and try to measure the differences between one of the labels, say person two's label, you can see that we can measure the difference and that the Euclidean distances are all pretty close to each other for the same label, yet distinct from different labels, which is an optimistic sign. And so this leads us to further study this in more detailed examples. But before diving into those examples, so we just looked at some small scale tests to show how this idea might work, but equally we have to consider how this idea might break, because every security system is designed to let some people in and keep some people out. And so for user identification, there may be cases where you have an adversary or some malicious user who's trying to impersonate a legitimate user, trying to pretend that they are someone else. And so we have to consider some ways that they might attack this, this technique. And so we define a few examples here. So for the impersonation attack, this would be a scenario where the adversary might try to mimic the holding style of the user. So how the structure is changed by the user's grip and force, they may try to imitate that through observation. Relatedly, there is the eavesdropping and replay attack, which we heard in some of the previous talks in different contexts. And the basic idea is still very similar, where rather than trying to imitate a signal by the user, maybe the adversary will try to obtain a copy of this signal by some means. And this can include by obtaining, say, a recording of the signal that's being played, and then they'll try to play it back with their own speaker and microphone to the target device in order to trick the identification system into authenticating them. And lastly, which is more of a disruption rather than an impersonation, is the jamming attack, where your adversary may try to sabotage successful attempts at identification by introducing noise into the system while we are sensing the user. And this can be conducted through, for example, playing noise or music while the user is trying to interact with their device through user identification. So with these considerations in mind, we outlined a sort of system architecture for our proposal, which we've named EchoLock. And so the act of performing this user identification through the structure-borne sound is conducted through four main stages that we've defined here, being signal transmission, pre-processing, feature extraction, and then finally hand biometric identification. And in the signal transmission process, we are utilizing the speaker and microphones that we mentioned beforehand. And we are transmitting what we call our N-chirp sequence, which is basically an acoustic signal that we've designed using a sequence of short chirp signals. And these chirps are inaudible, and by inaudible, we're utilizing the higher frequency ranges of 18 to 22 kilohertz. The choice for this is to minimize the amount of noise that can be perceived by humans and human hearing. After transmission, we can obtain this recording through the microphone and proceed into pre-processing, where we can apply some conventional techniques such as bandpass filtering or cross-correlation to eliminate any potential noise in our recording of the structure-borne sound, and then apply some signal segmentation to isolate our structure-borne sound from empty noise or airborne noise. And in doing so, we obtain structure-borne information about the device and the hand pressing against the device. With this signal, we can apply feature extraction by calculating a series of statistics within various domains in order to hopefully determine some metrics which we can use to identify a person. These statistics can be within the time domain, frequency domain, or general acoustic features, and we can calculate these and select features based on KNN feature selection, closest nearest neighbor. And so once we have our signal and the features that we want to use for identification, we can proceed into the actual hand biometric identification process, where we can perform optimal chirp selection by choosing the most transformed signals by the process of the hand exertion, and then perform geometry estimation to determine which identity produced these transformations in the signal, and then proceed on to our final profile prediction. And this profile prediction will be choosing from a profile database that we can build through a training process or an initiation process or enrollment process by any term that you may be familiar with, where the user can, during training or enrollment, they can hold a device and we can perform the sensing to build a database of samples that we know belongs to a specific user. And these samples are formed primarily by the hand posture and the device structure. So one of the key strengths of using the structure-borne sound as a credential is that this structure-borne sound information will be shaped by the device, yes, and by the hand, yes. But it is also a combination of these two factors, because the device and the hand combined produces a unique structure for the sound to propagate through. And this will be different if you were to, say, change the device or to have a different hand belonging to a different person, because different devices and different models are built differently with different dimensions and different materials. This will influence the propagation, but also different hands will have different properties as well, because their shapes are different. The size of their hand, the stretching of their fingers, the force that they exert, these are all unique as well. So the combination of the hand and the device acts as the credential in our user identification method. And so, that was the general architecture. To describe some of the details of how we're sensing in a bit more detail, we have our N chirp sequence, which, as I mentioned before, is doing a frequency sweep from the very high frequencies of 18 to 22 kilohertz. And we will be transmitting several of these chirp signals in sequence. And we'll apply some buffering in between these signals such that we can stagger the arrival of structure-borne sound and airborne sound. And to briefly touch on the physics of it, the structure-borne sound will be traveling much faster than the airborne sound due to the density of solid objects compared to air, which is less dense and less elastic. Now, and doing so by buffering, we can separate these chirps so that we can receive structure-borne sound before the arrival of airborne sound. And to detect this sequence that we're transmitting, we can prefix a pilot chirp in the beginning of our signal to aid in detection. This pilot chirp won't be used for measuring structure-borne sound, but merely we are designing it with such a unique characteristics that it can be easy to detect against the background of empty noise. And in doing so, we can identify the location of all following chirps in the sequence. And so you may also notice that I've been referring to this as an N chirp sequence before. So the N is referring to how many of these these chirp signals that we are playing in sequence. And depending on your choice, if you're using a larger N, say transmitting many chirps, or a smaller N, where you may be transmitting maybe 2 or 3 chirps, you'll get a sort of trade-off where by sending more chirp signals, you'll be collecting more information. But the trade-off is that you'll be spending more time waiting for the transmission and the collection process. So we will evaluate in our discussion the effect of choosing different values of your the lengths of your sequence. And for signal preprocessing, we're applying some conventional techniques that are standard for acoustic sensing applications, not just in user identification, where you can apply bandpass filtration to eliminate noise beyond your target frequency range. And then you can apply cross correlation to detect the location of your signal in the recording. In the transmission process, we essentially have two components: our transmission that we know that we sent out, and the recording that we know we received. Now, these two components, the transmission and the recording, aren't identical, but we know that somewhere within the recording is a copy of our transmission that has been slightly modified. So we can use cross correlation to detect where the similarity is strongest within the recording. For the feature extraction, we may obtain our signal, but we need to define some quantitative metrics that we can use to define differences that we observe. So, for example, in the time domain, these can be some statistics calculated about the amplitude in the time domain. So so common examples could be the average or the standard deviation of the amplitude. In the frequency domain, we can examine the spectral points, and there are also acoustic features such as the MFCC, the Mel frequency Keptrim coefficient, or chromogram, which are commonly used in music analysis, but we find that these traits can also be useful in measuring behaviors of structure-borne sound. And so on the bottom, these graphs that you can see illustrate how these metrics might be useful in telling apart different user labels for identification. So for example, on the left, in the time domain, if you were to visualize, say, three different metrics, the standard deviation, kurtosis, and range, you could see that by calculating these features and then plotting them in 3 dimensions, for 2 different labels, these samples are sort of clustered together in their own distinct regions, which means that we could potentially identify users by examining these statistics. On the right hand is the power spectrum diagram, where you can see the behavior of the frequencies in response to different users while they're holding the device. And you can sort of see some differences and some similarities because the act of holding a device is relatively uniform between different people, but you can still see the differences produced due to how different people like to hold the device. So for example, in some regions, you can see some stark differences, say between 18 and 19 kilohertz, where there is more pronounced differences between 2 users. But there are also some similarities between, say, 20 and 21 kilohertz due to the similarity of the action itself of holding the device, because there are only so many different ways a person can hold the device comfortably. So this outlines some different ways that you can distinguish between different users based on some of these features. And proceeding on to profiling, with the information that we are able to obtain, you can start to define some profiles for these different users. And so this relates to chirp selection. Now, we are transmitting several chirps, n number of chirps in our sequence, but it's possible that not every signal may capture detailed information while they are propagating through the structure of the device. And so we can perform a vector-based distance calculation where we can compute the difference or the degree of transformation between our transmitted signal and the chirp that we received by our microphone. And in doing so, we can select the most optimal chirps based on the highest degree of transformation in the recording. And continuing on, we can perform a geometry estimation where we can develop our own data structure to categorize our features for these optimal chirps. And then we can perform a calculation to determine which these features correspond to some specific label. And this label would be corresponding to a hand-device combination. So for example, if we were to collect a sample for an iPhone by a person named Alice or Bob, our geometry would indicate that this is a sample Alice from device iPhone, as an example. And with this, we can build a profile. And so using any sort of machine learning algorithm, you can perform classification based on the chirps that you've received. Now, in our case, we find that even classical techniques such as SVMs or support vector machines are sufficient to perform this identification. So we opt to choose these classical methods. And with the machine learning algorithm, you can perform the profile decision by outputting a specific label through a majority vote by receiving some number of n chirps and evaluating the geometry for each one of those. You can vote on which profile you believe was the source of these samples based on the geometry that appeared the most in each of these chirps that you've obtained. And so to continue on, and I'll try to wrap this up for the sake of time, we can perform some experiments to verify this idea. And in doing so, we can test some different devices and perform these tests in different scenarios, such as quiet or public spaces, and invite several volunteers to provide their own user samples. And so you can see on the bottom, we can identify some examples, such as different devices, the dimensions, and also the speaker and microphones, and how some people might choose to hold the devices. And so, of course, the key idea, like, does this idea even work? We can optimistically say, in general, yes, we can show that we can provide some reasonable true positive rates for user identification across different devices. So we can generalize this idea across different forms of hardware for different users and for different lengths of chirp sequences. And so that if we were to try this idea in, say, quieter office scenarios and louder public scenarios, we can also observe the performance. And for the public scenarios, which have a lot more, say, background noises, the sound of people walking or talking, and we can observe that there is some measurable decline in the performance, but it is not actually severe. And also the benefit of using the higher frequency ranges, say the 18 to 22 kilohertz range, is that these sound ranges aren't very common in everyday life. So we can minimize the amount of noise that can appear in our recordings by choosing these higher frequencies. We also examine a few other test cases, such as if you were to apply a case to your phone, or if you were to modify the shape of your hand potentially by wearing a glove. And at least in the examples that we've shown here, our solution is relatively robust. In fact, we don't observe a very significant decline in performance if we are testing these cases. Actually, on the contrary, in a few cases, we observe that the user identification accuracy is actually improved in some cases, such as by wearing a glove, which possibly may be due to cases where the glove is thin enough that it's fitting exactly to the shape of your hand, so it is not really disrupting the shape of or the structure of the device. And in doing so, it also minimizes the amount of microtremors in your hands that might influence the structure-borne propagation. Now, also critically, just to verify the security of the idea, we can also test the behavior of the attack models, such as through the impersonation attack. And to quickly summarize some of these observations, for the impersonation attack, where you might have a different person try to imitate the way a legitimate user is holding their device, we can see that we have a very low false positive rate, as only 6% for a simultaneous 90% true positive rate. So this shows that we can safely reject impersonators from our system. But also another observation is that it's rather hard for a person to sort of imitate a holding style just by watching a person from what we've seen, especially in the case of shoulder surfing, which is more common in other user identification techniques where someone might be watching you type in a password, for example. This isn't really as helpful for our case because watching over a shoulder, for example, you can't observe the hand very clearly. You can only see the device. Whereas watching from the opposite side of the user, there's only so much information you can learn about how much force a user is exerting just by watching them. So this shows that the system can be robust to impersonation attempts. And relatedly, for eavesdropping replay attack, we find that this attack is not able to succeed because in obtaining an acoustic sample of or acoustic recording of a structure-borne sound, you are actually obtaining really an airborne sound through your speaker and microphone. And if you were to play the signal back, you are truly playing an airborne sound by playing your speaker to the device's microphone, which means that you are losing all of the structure-borne characteristics of this information. Now, theoretically, it is possible to extract the true structure-borne sound if you were to somehow breach the device and then extract the sound file immediately. But in such cases, your device would already be compromised by the attacker, so you would have a lot more problems than just someone trying to imitate your holding style. And lastly, to wrap up some other considerations, regarding the length of your chirp sequence, there are factors that you can choose, such as how many chirp signals you are playing in sequence. And we find that transmitting more signals, a higher end value, is helpful, but only to a certain degree, because you start to get a certain diminishing amount of returns where transmitting more and more signals gets you less and less improvement in your accuracy. So we can see that even for a short number of chirps and for transmitting a very short signal, you can still get a reasonable degree of accuracy when trying to perform user identification. And also lastly, for jamming attacks, this is also a problem where noise can interfere with the acoustic sensing. And this is still an ongoing problem. It's still an open question that we are trying to resolve, but it is possible to detect these attempts by such as through thresholding, because you can sort of detect the appearance of frequencies that should not be expected when measuring your structure-borne sound. And also the position of your microphone and speakers on different hardware, because many different devices have their own specifications. We observe that you will get most likely the best performance if your microphone and speakers are far apart, say on opposite ends of the structure, like the bottom and top of your smartphone, for example, because this allows your transmission, the structure-borne sound, to propagate through the entirety of your device, which will allow us to gather more information about the user's hand. And so to wrap up, we've proposed this technique, which we called EchoLock, to perform user identification through the sensing of structure-borne sound, which will measure information about the user's hand geometry while it interacts with the structure of a device, which will change the behavior of structure-borne sound propagation. And this information can be useful as a credential for user identification. And in our tests, we can see that it is reliable sufficiently to perform some basic user identification tests. And it's also secure against some different attack scenarios like the impersonation or eavesdropping. So we hope this can serve as an interesting alternative to existing security in IoT. And yes, that's the summary of my talk. Thank you for listening. I'll take any questions if there are any.